Okay, now we're ready to talk about how to use the heap to implement the abstract data type for the priority queue. So here we have a min heap, and as we discussed, the smallest element in the min heap is always going to be at the root. So that's great. I can jump to the root if I'm trying to do a pop off that element. But then I got a gap to fill, so I got to somehow rearrange these and delete something, and I want to make sure I stay left filled so I don't have any gaps. Right now I've got a gap at the root. I also might want to be able to add something. So let's say that I wanted to push on a 3, right? So where should this 3 go here in order to maintain the heap condition? So I got to implement pop, and I got to implement push, and I got to do these efficiently. Now, you might be tempted to start thinking about this in a top-down way, because when we were doing binary search trees, all we had access to was the root, and we had to start at the top, right? So I might start at the top here and say, okay, 3. Is 3 less than or greater than 2? It's greater. Okay, so I got to go down to one of the children. So I don't know. I guess I'll go to the left one. Is 3 greater than 8? No. Okay, so maybe it should take the place of 8. But where does 8 go? I don't know. I guess I'll toss it down to the left. Okay, now that displaces 30, right? So where does 30 go? I guess I'll toss it down here. But where does 35 go? I don't know. I guess I'll toss it over here. And that kind of works out. But it turns out it's a little bit difficult to make that systematic. There's actually a much easier thing I can do if I add this at the bottom first and kind of work my way up. And I can do that now because arrays are random access. I can jump anywhere in this tree in constant time and work from there. So you remember the way that the tree is laid out, the last element in the bottom level is going to be the last element in the array. What I want to do is actually add this new element at the end of the array. So it's going to be actually right after the last element in the bottom level. So I'm going to add it there first. And so that satisfies the left filled condition, right? I don't have any gaps. That's great. But I'm violating the heap condition, right? Because this is actually less than its parent. It should not be less than its parent. And so what I'll do is, okay, if it's less than its parent, let me swap. I'll swap the 2. All right, so I'll swap the 10 and the 3 here. And then I check that with respect to its parent. Okay, so is 3 less than its parent now being here? Yes, so I have to swap those 2. And then finally, I'll say, okay, where did 3 end up? I swapped it up here. Is it less than its parent? No. So finally, we ended up with the 3 in the right place. Awesome. Okay, so let me do one more example of this. Let's say that I was to add, I don't know, let's say that I was to add a 1. Yeah, how about that? So I'll put the 1, or I don't know, no, let me say just a 5, actually. Okay. So I'll add a 5 here. And so again, I find the first available spot. There it is. And I look at the parent and I say, is that satisfying the heap condition? No. I need to swap them because 5 is less than 6. Now what about 5 with respect to its new parent here? Now we're good. Okay, so this is a proper min heap. So let's go try to implement that in code, right? So if I jump back to the code here, let me go to the push method and do exactly what I said. So the first thing is I want to put this entry, which is actually this tuple. I'm going to follow Python's convention. So it's a tuple. The first element in the tuple is priority. The second element is the data that's tagging along with this. So let me first put this entry at the end of the underlying array. That will be the first available spot in this data structure, right? So that's as simple as saying, whoops, it looks like, sorry, I need to put these in here real quick. That's as simple as saying self.array.append entry, right? But now I might need to fix some stuff up, right? Originally I would put something down here. Like I put the 3 down here, but that was wrong. I had to look at its parent. So I'm going to make a method called heap up a helper method, which is going to help me in other ways too later. So I'll just make it this helper method. And the purpose of this method is to keep bubbling the node, the node at I up until it satisfies the heap condition. So we recognize the data that's at node at index I could actually not be at the right place. And so we need to keep swapping it with its parents until it ends up at the right place. So here I'll just say, step 2, bubble up the entry until the heap condition is satisfied. So I'll just call that on the last index, right? So the index where this thing is at in the array. So I'll just say self.heapup len of array -1. Okay. So let's implement that now. So first of all, if I'm at the root, then I'm good, right? There's nothing above me, so I can't swap anymore. But if I'm not at the root, then I have to possibly do some work. So what I should be checking is, let me get the index of the parent, right? So I'll say parent is equal to self._parent I. So get the index of the parent, and if I happen to be less than the parent's priority, so I'll say it like this: if self.array. So if my priority, so remember these are tuples, right? Where the first element is the priority, right? So the first element in each of these data is the priority. So if the priority at this node that's stored at index I is less than the priority of its parent, so I would say then self.array parent 0, then I have to swap them, right? I have to swap the data that's there. So I would say self.array I self.array parent equals self.array parent self.array I. So this is the nice way that we can swap a sign in Python. So that's doing the swap. But we should check to make sure we don't have to keep going. So what we'll do is call this recursively, right? Because I saw this before. I had to swap 3 with 10, but then I also had to keep going and swap it with 6. So what I'll do is I'll recursively call this heap up on the parent. Okay, and that should be good. So I added some code here to draw this. Let me go ahead and try to add some data and see if this works. So what I'll do here is, maybe I'll just add a whole bunch of random numbers. So I'll say for x and np.random.randint, maybe I'll say between 0 and 100. Let me take 13 of them. And then I'll say t.draw, or I'll say, t.push x, and I won't have any data tag along with them yet, but this, remember, we can have data tag along with these. But the organization of the data structure only depends on the priority. Okay, so that's the important thing. Got that there. And now if I say t.draw, let's see what I get. All right, so let's see, is this a valid heap? So I added some random numbers to it apparently. And here's what they turned out to be. So looks like, okay, yeah, the minimum one is 9. And that is, if I look at any node here, it's always less than the nodes at the 2 children. Now notice actually we end up with duplicates, and that's fine. There's nothing here that said we can't have duplicates. But okay, so this seems like it's working so far. But now we have to implement pop. Okay, so we need to be able to take the thing off the top and figure out what to do. So if I go back here and I think about that, okay, let's say I popped off 2. I have a gap here. And I need to figure out what to do. And so it's like, okay, what goes in that gap? I mean, what should go in the gap is the smallest thing, right? I could look through the whole tree and find the smallest thing, but that wouldn't be very efficient. I want to do something more efficient. And it turns out what I should do is actually, it's kind of a similar thing. Let me go to the bottom of the tree and just promote the element there to be the root. And so notice I'm actually deleting a node, right, as I should be, because I popped something off. So I'm deleting a node and kind of moving its data up to the root. Okay, so this is now, again, a valid heap, right? Except I might be violating the parent-child relationship. And in fact, I am here. Okay? So I see that the 10 is actually greater, in this case, than both of the children. So I'm going to need to do a swap again. But I should be careful which node I'm swapping with. I actually have two choices here, right? So unlike when we were doing the heap up, we knew it was just the parent. We actually got a left child and a right child. So we got to figure out which one do we swap with. And so you always want to choose the smaller of the two, right? I mean, I could swap this with 8. But 8 is actually greater than some of the things over here, right? So 8 is actually greater than 3. And so I don't want to accidentally put that above here because that might violate the heap condition. So I'm always going to pick the smaller of the two children and do the swap. Okay? And so same kind of thing here. So now I got to follow along, and I say, okay, yeah, unfortunately 10 is bigger than both of its children. So what I'll do here is, yeah, again, I could try to say, let me swap it with 9, right? But 9 turns out to be bigger than 6, so that's not going to satisfy the heap condition. So let me make sure that I'm swapping with the smaller of the two. And then make sure that okay, this is, if it's the smaller of the two, this is actually smaller than the other child. And it's also smaller than the thing that I just swapped it with, which I had to do. Okay, so that's it. And now you see this is actually a valid heap. Everything is in the right place. And we have the smallest number at the top here. So let me just do that one more time. So let's say that it popped off the root here. So I got 3 coming out. And so again, I'm going to take the thing at the bottom rightmost entry, so the end of the array. Put that at the root. There's no longer a node down there. And let's see what I got to fix up. Okay, so 13, it's greater than both the children. Let me swap it with the smaller of the two. So that goes here. And again, let me swap it with the smaller of these two. That goes here. And we are good. Actually, let me do one more. Okay, let's say we remove 40. I think you can't have enough examples here. So let's say I was to, sorry, let's say I was to pop 6 off the top. Pop 6. And so I'm gonna remove that, and 40 is gonna get promoted. And now here, actually, I see 40 is greater than both these children. I'm gonna move this one to the left now. And then I'm gonna move it to the right. And then I'm going to move it to the left. Okay, and that should be a valid heap. All right, so let me jump back to the code, and we'll try to implement the pop method. And so we know that actually the first thing we should do is make sure that this array actually is non-empty. So I'll say len self.array is greater than 0. We can't pop off an empty heap. That doesn't make sense. We should make sure that throws an exception. Okay, but what we'll do is yeah, we're eventually going to return the data. Also, as part of this API, we're going to return the data associated to the element at the front. But we got to find that element first, and then we need to do some cleanup with heap down, right? Okay. So I guess actually first I'll say, okay, yeah, the thing that I want to return is it's the data at the first element in the array. Just remember, again, these are tuples. The second element in the tuple is the data associated to the priority, which is the first element. So I'll do that. That's the thing I'm going to return. Now what I'll do is I'll say, okay, self.array at index 0, that I'm going to make that take on the bottom rightmost data. So that would be the last element in the array. And then I can actually take off the last element in the array. So I'll say here, move the last element to the root. And then I'll say take off the last element. And so this is a list, really an array list that's implementing this. So I can just pop off the end in constant amortized time. So here I would say self.array.pop, I think it is. Let me actually double check. A list in Python, that should be pop. Yeah, okay, good. So you see that took that off the end of the list. So it turns out, yeah, we've actually in our underlying array here, we've got a method called pop that we can use to take off the last element. But the last thing we need to do is fix up the internal structure. And so we might need to perform a heap down to keep swapping this with one of its children. So I'll say self.heap down 0. Okay, so starting at the root, let's check to make sure we don't need to keep swapping stuff. So I'll implement this now. Alright, so what I need to do is get the children, the indices of the children. So I'll say self.children, I. And there might be no children. If there's only one element left here, which is the root, there might not be any children. Or actually, it could be in the middle of the thing too. So this will also be a recursive method, and there might just not be any children. So let me make sure that there's actually at least one child. And so I'll say, okay. Now let me think, okay, maybe there might be actually 2 children. And I'm not really sure yet which one is the smaller of the 2. If there happens to be more than one child, then let me see if the second child has a priority that is less than the priority of the first child. So in this case, it's okay. If self.array children1, if that priority is less than the priority of the first child, then I will actually make the child be that I want to swap with be children and index 1 here. Okay, so I'm trying to find the smaller of the 2 children. So make child be the smaller of the 2 children. And now I should check, hey, is the smaller of the 2 children actually less than the element at this index? So I'll say if self.array, if the smaller of the 2 children has a priority which is smaller than the priority at this index, then I need to do a swap. All right. So then I'll do the swap. I'm lazy, so I'm going to copy this code here. So I'll say let me swap child with I, and then I child. And I might have to keep going with the recursion here, right? So I swap those, but I might actually have to continue on. So then I'll recursively call heap down on that child to see if I need to keep swapping it with one of its children. All right, so hopefully I did that right. Let me try to test this out. So what I'll do is actually I'll pop everything off of this. So let's just try that. This is a while length of t is greater than 0. I'll say print t.pop, and I'll just put a space or maybe a comma in between. Oh, okay, and I was supposed to, it keeps returning none here. Right, it returns the data associated to this. So let me actually make the data associated to this be the priority. That's fine. And let me just say 2 n equals that. Okay. Great. Okay, so we started off with this tree like this, and it looks like it took off everything in order. And so actually this is something that we call heap sort. It's a sorting algorithm that we just got as a side effect of implementing this data structure. And so what we can do is add stuff to the heap and then remove stuff from the heap. And if we remove everything from the heap, well, we get everything that we put in coming out in ascending order. Now, the only thing I need to make sure of is I promised you at the beginning that we would find a data structure where push and pop were implemented in log n time. But they are, because if I look at this, well, this is almost perfectly balanced, except for maybe the last level. So this is even stricter condition than AVL. And we showed that the height of the AVL tree was big O of log n, where n was the number of the nodes in there. So we know that the height of this is going to be log, big O of log of the number of nodes in the tree. And so that means that, well, when we go to push something, we put it at the end, That's constant time, right? Because the array that's representing it has random access. And then we bubble this up. Well, the length of the branch is log n. So at worst, we're going to have to bubble this all the way up to the root, but that's going to be log n. By the same token, when we pop, we have random access to the beginning here. We take the thing off, and then we swap what was down here up. And we at worst have to walk all the way down by log n. So both push and pop have a time complexity of log n. And that's all there is to it. So it's a very simple data structure here that can be used to implement a priority queue. And that's why behind the scenes, Python's heap push and heap pop take a list as the first element here. They're basically doing the same thing that I just encapsulated in a class here, but they kind of just separate it out into these global methods that do push and pop. All right, so I'm just going to have you crunch on that for a second. But then there's one last thing that I want to show, because this isn't enough, and actually Python's implementation is not enough if we want to update the priorities of some of our data, which we're going to need. Okay, but we'll pause for a second and let that sink in. Wait, one more thing I want to mention. So because push and pop are log n operations, for heap sort, when we push everything on and then pop everything off, this is actually an n log n sort. So this is another n log n comparison based sort. You can see we're doing all the comparisons here, right? In heap up and heap down. So we're doing comparisons. And it's log n just because, the push operations each take, at most the tree has n elements in it, so it's going to take log n for the push. And then for the pop, it's got at most n elements, so that's going to take log n per pop. And we do that n times, right? So for each element. So that's an n log n sort, another n log n sort. Maybe the disadvantage of this sort compared to merge sort, which is also guaranteed n log n, is it doesn't have the best cache locality. So what I mean is, if we look at the indices of the elements that are next to each other, and then we look at the index of the parent, these get further and further apart the further you go down. So notice there's a bigger difference between 11 and 5 than there is between 5 and 2. So the more levels that you have, the further away your children are from the parent in the array. So you end up jumping around the array a lot. And that's not good if you have a really big heap, and because you'll have to jump pretty far to get from a parent to a child or from a child to a parent. And that doesn't work well with the computer architectures that we have that assume in their cache, when they kind of say, hey, you're loading this element in the array, I think you're probably about to load the next 10 elements maybe. I'm going to take those 10 elements into faster memory. That doesn't work so well in a heap. So that's the one downside of a heap. So we say it has bad cache locality. So you might, even though theoretically this is also an n log n sort guaranteed, it may not be the best sort in practice compared to merge sort. Okay, so just something to look out for.